Justin Miller, Oxford Physics here, and here we go. So we've looked at Ohm's law, we've looked at resistance, the measure of the opposition to current. Now we want to go ahead and start to investigate a little bit deeper what we can do with resistors. So just like capacitors, we can put resistors in different types of configurations. Series configuration, parallel configuration, combination configurations. And we can start asking about what's the potential difference across each resistor and what is the current through each resistor. So we're capacitors, we were worried about the potential difference in the charge stored. Resistors, it's the potential difference in the current through. So go like this. Resistors, in series and parallel configurations. Series, well, what do we have? We've got that they're all on one branch, all on one pathway here. We can say we've got ourselves an R1, an R2, an R3, and this could keep on going. We've got R up to R sub n. That's it, a bunch of resistors in series. So there's what series configuration looks like. What are some things about series? Well, because there's only one pathway, the current has to be the same through each resistor. Got this. I1, I2, I3. I1 is equal to, I2 is equal to, I3 is equal to I. Current is the same everywhere in a singular branch. I'll just say in a given branch. So this would be assuming that, yeah, this is hooked up to some source potential and things of that nature. Well, what else would we have in here? There has to be some sort of source potential that's driving the current, and we can define something like this. We've got ourselves a delta V1, a delta V2, and a delta V3. Well, the potential differences across the individual resistors does not necessarily need to be the same. It depends on the resistance of the resistors themselves. So when we go to something like this, we could note that each resistor has its own definition. We've got that R1 is defined by delta V1 divided by I1. R2 is defined by delta V2 over I2, and R3 is defined by delta V3 over I3. Well, again, if the currents are all the same, I1, I2, and I3, those will all just be I, so I can take off those subscripts there because they're in series with one another, which then means delta V1, delta V2, and delta V3 would all be different potential differences, assuming that R1, R2, and R3 are different amounts of resistance. There it is. So what does that mean? Well, it ultimately means that there's some overall potential difference across this entire portion here, which I could call like a delta V total, and that's going to be equal to a delta V1 plus a delta V2 plus a delta V3. The total potential difference across the whole section is the sum of the individual potential differences across the individual resistors. That has to be the case by the conservation of energy. So that's basically that. This is how resistors behave in series. Now, if we wanted to go ahead and say, what else could we do with this? Well, we could think about taking these three resistors and putting them together and saying we just got one overall resistance. Ooh, excuse me. So let us replace these resistors with one singular resistor with resistance Req. Equivalent resistance of system, or at least of that portion right there. Well, what are we going to do with this? How can we figure out what that equivalent resistance is? Well, let's draw it out first. And say we're going to take those three resistors, we're just going to really press them together. So we've got this 1 over all resistance Req. Whether we've got three separate ones or just one, if this singular one is supposed to do the same thing as the others, we have to have that the current's the same. So we have I total is just I, the same I that's up here, same current. Well, what else would we have to have? We would have to have that this here is delta V total, which is, again, delta V1 plus delta V2 plus a delta V3. Again, we can do it for 2, 3, 4, 5, 20,000 resistors in series. We're just doing it for 3 right here. So, if we went ahead and said, well, what do we have with respect to this particular resistor then? Well, if we defined its resistance, Req, as being equal to delta V total divided by I. So there we go. We've got the equivalent resistance there. Well, how are we going to get this out of those? What do you notice? Well, they have the common denominator of I right here. What happens if I think about adding those three resistances together? R1 plus R2 plus R3 is going to be equal to delta V1 over I plus delta V2 over I plus delta V3 over I. They're all over I, so I can write this as delta V1 plus delta V2 plus delta V3 divided by I, which is delta V total divided by I, equals delta V total divided by I, which is Req. So what's the bigger picture here? Hey, when we have resistors that are in series, the equivalent resistance of that band is just the straight across sum of the individual resistors. Resistors add straight across when they are in series. So, for resistors in series, the equivalent resistance is equal to the sum from I equals 1 to n of R sub I, which is just R1 plus R2 plus dot 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 plus R sub n. And what else do we have? I1 is equal to I2 is equal to I sub n, same current everywhere, and then the potential difference gets split up amongst the individual resistors depending on what the current is and what the resistance of the individual resistors are. This is just, I don't want to say the opposite, but this is the way that capacitors added in parallel, right? They added straight across when they're in parallel, or resistors add straight across in series. So we'll come back to why that is, but it's just something that we've got going on there. All right, so there's series. What else do we want to do? We want to do parallel. So let's consider parallel. Parallel case. Parallel case requires a little bit more care, but ultimately, we've got this. And This would be an R1. This would be an R2. If we drew in some current, we're assuming this is connected to some source potential, we would have some I total coming in. Then what happens? We've got, it splits up because there is a junction right here. Takes two paths there, splitting up. What do we have to have? We have to have that I total is equal to I1 plus I2. Conservation of mass, conservation of charge. Ultimately, whatever goes in has to be split up. There we go. So what else do we have? Well, similarly to what we had with capacitors, if we started to think back and trace these terminals of the resistors back to the source potential, both of them would equally be connected to that source potential. Likewise on this side, both of them would be equally connected to the source potential's negative side, say, and thus we must have then that we have a potential difference delta V1 there, potential difference delta V2 there, where delta V1 is equal to delta V2. Since they're in parallel, they have to have the same potential difference, just like capacitors, same sort of correlation there. So, now we come to the point where we say, you know what, we want to replace these two resistors with one overall resistance. Instead of having these two separate pathways, we just want to have one. So how are we going to go ahead and do that? So, we'll draw out the equivalent system here. And we've just got this. Well, if we take these two and meld them into one, we just have one total current, right? We're not going to change the current. So here we still have ourselves I total going through. We've got ourselves Req is the resistance of this resistor. And we have that the potential difference is equal to delta V1 is equal to delta V2, which we can just really call that delta V. Delta V. So there we go. Well, let's go ahead and go back to the definitions of the individual resistors and compare them to the definition of the equivalent resistance and note what we have going on here. So here, we've got that R1 is going to be defined as delta V1 over I1. But delta V1 and delta V2 are the same, so I'm just going to call this delta V divided by I1. And then we've got the R2 is going to be defined by the same delta V divided by different current though. Delta V divided by I2. So there's the two individual resistances in terms of the currents through them and the potential differences across them. Come over to this one. We've got ourselves that Req is going to be defined by delta V divided by I total. Delta V divided by I total. And what do we know about I total? Well, we've already said. I total has to be equal to I1 plus I2. So that breaks up. Well, let's look at it in this term. What's the same between these three expressions? And you say, well, it's the same potential difference, right? So let's think about inverses here. 1 over R1 is I1 over delta V, 1 over R2 is I2 over delta V, and 1 over Req is I total over delta V. Then if we try to make a correlation with those and build Req out of those, we should be able to see this, that 1 over Req is equal to 1 over R1 plus 1 over R2, because that will be equal to I1 over delta V plus I2 over delta V, which is equal to, well, I1 plus I2 is I total divided by delta V. And that's what we've already said that 1 over Req would be equal to, equals 1 over Req. So, in terms of them adding in a parallel then, or parallel, we have that REQ is equal to the quantity of the sum from I equals 1 to n of 1 over R sub I to the negative 1, which is the quantity of 1 over R1 plus 1 over R2 plus dot 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 plus 1 over R sub n to the negative 1. Inverse of the sum of the inverses. What do we have? Well, delta V1 is equal to delta V2 is equal to delta V sub n. And there we go. Potential differences are all the same when they're in parallel, and they add the inverse of the sum of the inverses. And when they're in series, the currents are all the same, and they just add straight across, which is directly switched from what we had with respect to capacitors. Why? Why is this switched? And it comes down to this. This is opposite with respect to CEQ. Why? Well, C is defined as what? Q divided by delta V. R is defined as what? Delta V over I. This one is inversely proportional to delta V. This one, the resistance, is directly proportional to delta V. Okay? It's sort of an inverse relationship between those two relative to delta V. So what happens? It switches the way the rules are, the way that they add together for the equivalent systems. Because again, inversely proportional to delta V, directly proportional to delta V. That's it. Q and I, kind of the same correlation. Q is the charge separated. I is the moving charge per unit time. But that's it. It comes down to the potential differences. There, start out a little bit more. All right, so that's what we've got, series parallel. Pretty easy to deal with singularly. Same sort of correlation, same sort of systems that we dealt with capacitance. Just we're talking about current instead of charge now. And resistance instead of capacitance. And what else can we do with this? Yeah, we can put them in nice big systems with both series and parallel configurations together and make one big nice circuit that has combination. Series and parallel. What do we want to do with it? Figure out everything about it, just like we did with capacitors. What's the current through each resistor? What's the potential difference across each resistor? How do we do that? Collapse it all down to one, and then build it back up until you know everything about everything. And that's it. We'll come back and do a problem. Just wanted to get this all introduced. That's it. Take care.